I'd like to start out by talking about the four forces. And I want you to think of these as fields that transmit bundles of energy in wave packets. Now, that's true for all the forces except gravity. We are still on the hunt for these waves called gravitons that, or gravity waves that transmit gravity through space. There's still no evidence of them, but they continue to hunt for them. Now, the first force is the strong force, and as you can see here, it's the force that acts on the nucleus. This is a picture of the nucleus with the neutrons and protons in them. And this is 1 femtometer in length here. So we're talking about very small sizes. 1 angstrom is equal to 100,000 femtometers. And of course 10 angstroms is equal to 1 nanometer, and they're 1 times 10 to the 9th nanometers in a meter. So we're talking about something rather small. And as you know, the strong force also works on the quarks inside the nucleus. Now the strong force is as it implies, is a very strong force, but it operates over very small distances, as you can see here in the fact that it's on the atomic level. We're looking at a nucleus here. The second force is the weak force, and this governs radioactive decay. In particular, we're looking at beta decay here. Beta decay is a case where you go through and convert, or a neutron is converted to a proton, and electrons spontaneously is ejected along with an antineutrino. I don't think we've talked about antineutrinos before, but it's another anti-particle in an array of antiparticles of the neutrino. And the neutrino is a very tiny particle. In fact, billions of these things go through the Earth constantly without even striking another piece of mass. So, get some idea of the small size of neutrinos if they can pass through the Earth without hitting any matter. So that's the weak force, and again, it's governed over a very small distance, or its field, I should say, operates over a very small area. But it is again a strong force too, and a small force over a very small area. I mean, a strong force over a very small area. And then one that you're probably all familiar with, this is the electromagnetic force. And the electromagnetic force governs electrons and protons. That is, it keeps the electrons connected to the nucleus through the positive charge on the protons, the negative charge on the neutrons. And the electromagnetic, not only does it have to do with charged particles, but it has to do with the magnetic and electric fields and photons, which are all part of the electromagnetic spectrum. And the electromagnetic force also is a very strong force, but again, over a very small distance. And then finally we have gravity, and this is the weakest force by far and away. And gravitational force, as you can see by this formula, it's Newton's law of gravity. Force is equal to the gravitational constant times the mass of one body times the mass of a second body divided by the square of the center of the distances. So one of the things that comes out of that equation, and you probably already know this, is that gravity is proportional to or inversely proportional to the square of the distance. And it's proportional to the mass of the bodies. So gravity, the farther you get away, the less gravitational pull there is. Now gravity, even though it's a weak force, it operates over great distances, infinite distances, if you will. And as a consequence, we'll talk more about this later on, but gravity may be siphoned off by other dimensions. When we get a little further in, I'll tell you more about that interesting episode. I want to show you a video right now taken by David Scott, who was on the Apollo moon mission 15. And what he's going to do here is he's going to drop a hammer and a feather. I'll let him tell you more about it. but this is to show that things fall back to Earth at the, or in this case, the Moon, at the same speed, which is something that Galileo came up with some time ago. People think that he dropped objects off of the Leaning Tower of Pisa, and they fell to Earth, and he showed that they fell at the same rate. Actually, he didn't do that at the Leaning Tower of Pisa. He did that in his laboratory by rolling balls down inclines and timing the length it took. So let's see what David Scott has to say. It's a kind of a silly little video, but I thought you might enjoy it.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the Moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
Now, scientists are very much, I wouldn't say disturbed, but physicists are a little upset that we have four forces. They would like the world to only be one force. It seems more symmetrical to them. After all, back in the 1900s, Maxwell found or discovered that the magnetic and the or electricity and magnetism were related through the electromagnetic force. And so here is a combining of what were thought to be forces into one force. And scientists kind of like the idea of maybe one of all the forces being together at one time. And they suggest that perhaps in the high energies of the Big Bang, something called gauge fields, or if you will, Yang-Mills fields, we'll show an example of one of those later on in the Higgs field. These may have governed how the four forces might have been united in the high energies of the Big Bang. And we have some evidence of this in the electroweak force. The electroweak force was proposed in the 1970s, and the guys that you see here proposed not only that the weak and the electromagnetic forces were combined at the higher energies of the Big Bang, or shortly after the Big Bang, but they also predicted that some particles would exist that we didn't know about in the 1970s. And subsequently, those particles were found, and so the three of these scientists won the Nobel Prize because it substantiated the fact that the electroweak force was united, that is, the weak and the electromagnetic were united in the high temperatures of the Big Bang. And they won the Nobel Prize, Glasgow, Weinberg, and Salem here. Well, now I have to emphasize, though, that the temperatures were great. We need tremendous temperatures to unite these forces. We'll get into energy levels in just a second, but we're talking about 10 to the 15 degrees Kelvin. It's believed that the electroweak and electromagnetic and weak forces were united in the Big Bang. There's also something called grand unified theories, and these are efforts to unite the electroweak and the strong force at even higher temperatures back in the Big Bang. So before the electroweak energy or electroweak force broke out into its electromagnetic and weak force, we had the electroweak force combined with the strong force in these grand unified theories. Now there's a lot of these things floating around, and nobody's really sure 100% which one of these theories is correct, or if any of them were correct. And unfortunately, because this occurred at such high energies, we're going to need to generate some of those extreme energies here on Earth, and it's not possible to test this theory yet with duplicating the high energies in the Big Bang. Maybe sometime we'll have something like the Large Hadron Collider that'll be able to smash particles together and get the kinds of energy levels that existed when it's proposed that these two forces, the electroweak and the strong, were united in the Big Bang. But in the meantime, we do have a prediction from grand unified theories, and that prediction is that the neutron would decay. Now, neutrons are notoriously stable, so I don't think we can look anytime soon seeing neutrons decay. People are out there looking to see if neutrons decay, but you have to look at billions at a time and hope that one happens to decay, because the length of time is, I don't know the number, but it's billions of years it requires for a neutron to decay. So it remains fuzzy, this guts that is grand unified theories. And then if you go even further, there are many physicists want to unite all of the forces, and you'll see why this works out nicely when we talk about symmetry. But there is the idea that gravity and all the other three forces were united in even earlier times in the Big Bang at unheard of energy levels before they were separated and came out during the Big Bang. And that's called the theory of everything. And it's simply hypothetical at this time, but perhaps you've heard about string theory. String theory is an effort to explain how the four forces might be united in the energy levels of the Big Bang. So we've got these energies, string theory predicting that these forces would be together at those highest energies. But a problem with string theory is that there's no way of getting around it unless you try to make the universe have 11 dimensions. So now we have to have 11 dimensions. It's possible. They're even talking about maybe some of these dimensions getting caught up in the fabric of space-time, rolled up inside the fabric of space-time. I have no idea what that precisely means. I'm not sure they do either. But there may be these other dimensions out there that we don't know about because they're so small in our universe. And if string theory turns out to be correct, then that explains why gravity is so weak compared to the other forces, because it shows that gravity is being siphoned off, some of the energy of gravity is being siphoned off into these other dimensions. And so here in our space-time dimensions, we're only seeing part of the strength of gravity. But we're a long way, it seems to me, from deciphering whether string theory is true or not. Now, I mentioned the Yang-Mills fields, and I want to talk specifically about the Higgs field, which was proposed in the 1960s. And this is a mysterious field that permeates space, and it actually tells particles how to behave, and it also gives them their mass. So this is not hypothetical anymore. The Higgs field was proposed in the 1960s, but in 2012, the Higgs boson, the so-called God particle, was actually discovered by the Large Hadron Collider. You probably read about it in the news. And so once the Higgs boson was discovered, that completed all of the particles, that is, all of the particles that come from the standard model of physics have now been discovered. And the Higgs field predicted all of those particles. And of course, they had to give some Nobel Prizes for that discovery, and they did, to Peter Higgs and Francois Engler, who proposed this in the 60s, along with Robert Brout. Unfortunately, Robert Brout died before the Nobel Prize was awarded, and they don't give Nobel Prizes posthumously, but he certainly deserves credit for some of his work. So the God particle was discovered, and this tells us that there is this mysterious field that permeates space and tells these particles how they should behave. And so it's really cool when scientists can derive equations and make predictions about the universe we live in, and then we actually find that they're right. That's very exciting. And when the Large Hadron Collider discovered the Higgs boson, well, the physics world was set on fire with that discovery. Now, one of the cool things about the Higgs field is that it can explain how all of these forces are united in the Big Bang. if the Higgs field is 0, then all of the forces will be united as one. And then as the universe cools, well, we think we had symmetry breaking, and these forces came out of the Higgs field and were, or I should say, they were broken out from one force to 4 forces, and the Higgs field went from 0 to some other value, and whatever that value is determines what how the forces behave. So that's how the Higgs field relates to the forces. Get more into this in just a minute. Now, I just threw this particular slide in. I'm not going to ask you any questions about this later on, but I did want you to see all of the particles that have been discovered because of, or that were predicted and have been discovered from the work that's been done over the last decades. You can see here the quarks. There's 6 types of quarks. We talked about the 6 quarks, or we've talked about quarks. They're the particles that go together to form the protons and neutrons. And you've got the leptons, which we've discussed before. Primarily, we've discussed the electrons. And then, of course, there's the Higgs boson and other bosons there, including the gluon, which the Higgs boson, of course, being the one that was just discovered. So this completes all of the particles in the standard model of physics. And I want to also point out that you're seeing all the particles, except that you have to recognize that there also exists antimatter of these particles. So each one of these particles has an antiparticle, except for a photon. A photon is not negatively charged. A photon is itself. But all of the other particles have antimatter that's the opposite charge of what these would be, except for a photon. The antiparticle of a photon is a photon. Now, the reason that I say that these get matched up is you've heard me mention before virtual particles. We have in vacuums, and I know this is really hard to grasp, but we actually have the creation of particles in vacuums. We think of perfect vacuums as being empty of everything by definition, but vacuums actually produce these virtual particles, and they come in pairs. I think we talked about this earlier. They come in a matter and an antimatter pair, so it might be an electron and a positron being the positively charged electron. So then they instantly destroy each other. And these are basically quantum fluctuations, which we're going to talk a lot about here very shortly. These are quantum fluctuations in the vacuum. So vacuums are not perfect, even though you've been told that. So I thought you'd like to see all the particles that exist out there. It's been a very, very successful model. That is the standard model. Now I want to switch gears here a little bit because I want to talk about symmetry. We need to talk about symmetry breaking, and I've got to explain symmetry in order to talk about how it gets broken. You probably all know what geometrical symmetry is. This is an actual picture of an ice crystal, a snowflake, and you can see these things turn into very special things. When we talk about geometrical symmetry, it means we can rotate this crystal 60 degrees, and we're not going to make any changes to the snowflake. It still looks the same even though we've rotated it. So we say it's symmetrical with the 60-degree rotation, or you can do 180 degrees, or you can flip it. So all of those things make this snowflake symmetrical. Crystals tend to be symmetrical. There's a whole field in mineralogy that talks about all the different things you can do to crystals based on the symmetry of the way they've grown. Now physicists like to talk about symmetry in terms of translation, or it's called translational symmetry. And this is basically going and performing an experiment in one part of the room and then running over and performing that same experiment with the same results in another part of the room. And that's called a transformation through space type of symmetry. You get the same result, and you know, it's really basically just saying that the laws of physics are the same everywhere, and you can have a time transformation, or a transformation through time, where you can do that same experiment at one point in time, and then a little bit later on you can do the same experiment and you get the same result. So basically it's saying that space-time, the laws of physics are the same in space-time. Now the catch here is, and then this bothers physicists, the catch here is that you can't do that with the forces. We've got these four forces, and they behave differently, and that bothers physicists. They want to see some symmetry there, because we do see symmetry in almost everything we do in the world of physics, and yet the forces don't seem to be symmetrical. And this goes back to Einstein's day, where people have been talking about the unification of the forces. And as I mentioned, you can unite the forces potentially under the great energies that we had in the early parts of the Big Bang. And the way that those forces came out of being one force and broke down into the other forces was through something we call symmetry breaking. So I'd like to go into a little bit about the symmetry breaking and how it might happen. But in order to do that, I've got to explain the Mexican hat. And the Mexican hat is just a nice way of looking at energy levels. The z-axis here is energy, and the x and y axis, which are 360 degrees on the Mexican hat, those are bond directions. Now, to make this simple, I want to talk first about how crystals relate to the Mexican hat. You can see these are amethyst crystals over here. Very nice crystals. They have a symmetry to them. You know, the crystal faces. But the physicists go, and I don't have this kind of mind, I'm not a physicist, but physicists look at that and they go, how come they chose that direction to grow in? I mean, they could have grown this way, they could have grown that way. How do we know what way, or why do they choose that particular way? And that's where the Mexican hat comes into play. And what I'd like to do is to just go through how water, as an example, how water goes from high energies and then is forced to choose what direction those crystals are going to grow. So at the dashed blue line up here, we're going to have water as a liquid, and the water molecules don't have any preferred direction. So they can point in any direction. They have basically they're free to point in any direction they want. But as the energy gets lowered and it comes down to the top of the hat, well that's the freezing point of water. And at the top of the hat, then we're going to have a phase change. We're going to go from a liquid to a solid, and when the ice forms, that's when basically nature's saying, choose a direction, ice. You got to choose which way you want to grow, and the way it rolls off of the top of the Mexican hat is the direction that it takes when it starts to crystallize. Now, I'm going to show you a really cool film here, and in this film, let's go ahead and take a look at it. In this film, we've got ice crystals growing out of water. The first thing to note is that when we bring this down, you don't all of a sudden have the whole, all the water freeze. You have individual points in the water that form crystals, and you can see them in this film. They're forming in different locations, and that's because they're reaching the top of the Mexican hat at different points in the water. They're hitting that freezing point, they're coming out, and then nature's saying, hey, you got to choose a direction, and the way that they fall off of the Mexican hat forces those crystals to choose a direction. Now, if this film went through and showed you the entire crystallization of the water, you'd see all of these different crystals running into each other and bumping up against each other, and that's because they're all growing in different directions, because they've fallen off of this Mexican hat in different directions, choosing different directions to grow in by the way they fall off the hat. Now, it turns out that we can actually, and by the way, this phase change from liquid to ice, we call that a spontaneous symmetry breaking. It's also a phase change when you talk about water to ice. And we're going to talk about that spontaneous symmetry breaking with the Higgs field. It's basically the same principle. Physicists believe that we can use the Mexican hat to explain what happens to the Higgs field in the early beginnings of the Big Bang. And that's essentially that you have the Higgs field up here at very high energy levels at the Big Bang. And then when those energy levels are decreased, you get down to the top of the hat. Now that top of the hat is going to force the Higgs field to decide which way the forces want to come out and break apart. So think of it as the Higgs field is at 0, a value of 0. The forces are all as 1, and then when they hit the top of the Mexican hat's saying, look, you got to choose which way you want to go here in terms of forces, and the forces break out, and it's believed that their physical properties are related to the way they fall off of this Mexican hat. So not only do we have spontaneous symmetry breaking at the top of the hat, but we also have the forces going through somewhat like a phase change. We're going from one force to more than one force during this process. And I hope that this kind of gives you an idea of how then the universe might have gone through the symmetry breaking, and explaining how we might have had one force together at high energies, but as we lowered the energy, we had spontaneous breaking of symmetry and the forces starting to come out, and the Higgs field value taking a value other than 0.